All right, here are perfect problem 2 solutions for math 211. 5 different questions here, which will test, I guess, both your knowledge of kind of the language of sets, what all these symbols mean, and then how to kind of deal with Venn diagrams. So what we're told here is that we have these sets A, B, and C, and that the number of elements in set A is 50, and the number of elements in set B is 43, and the number in set C is 29. What the question is asking is, what is the largest that what's the largest number of elements that could be in the union of A, B, and C? And what's the smallest number of elements that could be in A, B, and C union? So let me see if I can kind of draw some pictures that would correspond with those two cases. So I guess I'll first take care of A. What is the maximum possible value? Well, if you want as many things as possible in the union, you kind of don't want anything in the different intersections, because when you put elements in the different intersections, then they'll count for both of these sets. Or if I put them in the intersection of all three, they'll count for all three. But if I want to make the union as big as possible, I don't want any elements in these intersections. I want none here, none here, none here, none here. I want all 50 from set A over here, and all 43 from set B over here, and all 29 from set C over here. So the number of elements in A union B union C in this picture would be 50 plus 43 plus 29. Let's see, 29 and 43 is 72. 72 and 50 more is 122. Okay. And then we'll kind of compare that with part B here, where we're sort of going for the opposite. What we want to do in part B is have as few as possible total elements in the union of A, B, and C. So really our goal in B will be, instead of trying to keep everything out of the intersections, we're going to try to put everything into the intersections. So being in any intersection will help, but being in this special intersection will count for all three of them. So I'm going to put the largest number I can right here. Well, I only have 29 elements in set C, so at most I can put 29 here. This is set C down on the bottom, and the minute I put 29 here, it means there's 0 here, 0 here, and 0 here. And so now I'll think about set B over here. That's got 43 elements. So if this is set B, it's got 43, but I already used up 29. And so if there's 29 there and 43 possible, then the most I could put here will be 14 more, which would leave 0 here. And so now when you're considering set A, you're like, well, I got 14 of them and 29 more of them already. I got 43, but I need 50, so I guess I need another 7 over here. So if we want to make the union of A, B, and C as small as possible, I would go with this picture here, and we'd have a total of 50. All right, what about part C here? Well, we're going to end up doing the same thing, so I'll go ahead and draw the picture first. Not the best picture, but I guess it'll work. I'll draw my sets. I'm going to make that set A. That's set B. And here's set C down here. And so in this problem, I'm told that the intersection of A, B, and C is 10. So I have exactly 10 elements right here. And now I'm asked, what is the minimum possible value of the union of all of them? So I'm looking for a picture kind of like this, but it can't be exactly this picture because I put 10 right here. So now I got to think about where I'm going to put the rest of the elements. Well, let's see. I want to end up with, maybe I'll write them down here for reference. I'm going to want 29 here, 43 here, and 50 here. Okay, so there's a few different ways you can solve this. It might be a guess and check, might end up being the most useful for people. But I'm going to start with this 29. So I want 29 down here. Ideally, I would put 0 right here, because I want as much stuff in the intersections as possible to make the overall union as small as possible. So how many? I need 29, which means I need 19 more here and here. How many should I put in each little bin? So the trick to that is to kind of look ahead. I want there to be 50 here and 43 here. And so I already got 10 of those used up on both, but the key point is that this circle should have 7 more than this circle. So when I consider how I want to allocate my remaining 19 elements here and here, I would like to have 7 more here than I have here. So I need two numbers that add up to 19, so that the bigger of those two numbers is 7 larger than the smaller of those two numbers. I think there's a way to do that. I think 13 and 6 will work. I think if I throw a 13 here and a 6 here, things will work out really nice. Because first, note that I have 29 in C, just like I wanted, which is good. And then if you think about B, I want 43 total here. So ideal would be if I could put a 0 here. Am I going to be able to do that? Well, let's see, if I want 43 total, I've used up 16 already, so I would need 27 more. And now that gives me 43 in B. And because I allocated this 6 and this 13 so wisely, the 13 and the 27 gives me 40, 10 more is 50. I don't need any over there. So what I've managed to do is draw a picture that has 10 in the intersection of all three that kind of didn't waste any in any of these sets. So this must be an optimal solution. I got the number of elements in the union of A, B, and C is equal to 13 plus 6 is 19, plus 10 more is 29, plus 27 more is 56. So not quite as good as this picture, but still pretty good. Right? 56 is a pretty small number. I kind of didn't waste any, is one way to think about this. Okay, fortunately, I think that was the hardest one that I just did. So let's go through and knock out D and E. For part D, same thing. I'm going to need a picture, so I'll go ahead and draw it ahead of time. I'm going to do the same thing. I'm going to assume A is up here in the top left, and then B is right next to it, and then C falls down there. And for part D, I want the intersection of A and B to be the same as the intersection of A and C to be the same as the intersection of B and C. In other words, I want 10 in each of those intersections. So the question becomes, what is the minimum possible value of the union? Well, I guess if you think about kind of the maximum choices, I could either throw 10 here in the middle of all three, and then I'd have 10 in each of the intersections, or I could put 0 there and 10 here, here, and here. So it's kind of one of those two choices, either a 10 here and a 0 here, here, and here, or I could put 0 here and 10 here, here, and here. Note that either way, I'm satisfying this criteria where the intersection of A and B is the same as the intersection of A and C, which is the same as the intersection of B and C in terms of their cardinalities. They're all equal to 10 in these two pictures. But with all this information in here, I can just go through and fill in the rest. I need 50 total in set A. I've used up 10, so there'd be 40 here. I need, I don't remember the number, 43 total in set B. I used up 10 here, so I'd need 33 here. I need 29, I think, total in set B, so I put 19 here. And that would make that work. If I were adding these up, I'd have 40 plus 33 plus 19 plus 10. That seems pretty good. Let's see if that beats this case. So down here, I've used up 20 already from set A, so there would only be 30 left behind. I've used up 20 already from set B, so there would only be 23 left behind. And I've used up 20 from set B, so there would only be 9 left behind. And I think if you figure out the number up here, you'll actually have more. A union B union C. 40 plus 33 plus 19. Well, let's see. 19 plus 33 is 52. And 40 and 10 is 50. And 50 and 52 is 102. Whereas down here, I got the number of elements in A union B union C is 30 plus 23 plus 9. 9 and 23 is 32. Plus 30 more is 62, plus 30 more is 92. So I was looking for the minimum possible value. This looks like the better one. So this is my answer. And maybe I can just kind of go through and cross this out. I'd like to keep it legible because it kind of shows my work. This is not optimal, whereas this one ends up being optimal. So I'll call that my answer to part D. All right, part E, last one. So for part E, again, let's go ahead and draw the picture. And this one, it's a lot of understanding the notation. Start out with A, take away the union of B and C. That should be the same as if you start out with B and take away the union of A and C. And start out with C and take away the union of A intersect B. All of those are 10. What those are referring to is this region, and this region. So now what I have to do is fill in all the gaps in order to make the union as small as possible. Okay, so I'd like to put as much stuff in the middle as possible like I've been doing, but I know that I only need 29 total in the bottom here, so I could throw... Tempting to put all 19 in here, but we're going to run into the same problem that we ran into up here. If I put all 19 here, then I'd have zeros here and here, and then when you consider sets A and sets B, they're going to be the exact same size, right? They have this 0 and 19, 0 and 19, and whatever I put here will go into sets A and B. So that's going to be bad because I know that set A over here has to be 50 and this has to be 43. So this one has to be 7 bigger. Well, in order to make this 7 bigger, I better stash a 7 over here and a 0 here, and now go through and fill in the pieces. Well, let's see, I've used up 17 of the 29, so I can throw a 12 here. And now I got 10 and, well, let's do this one. The numbers will work out better. 7 and 12 is 19. Plus 10 more is 29. If I throw a 21 here, I got 50. And I think that'll make everything check out. 21 and 12 is 33. Plus 10 more is 43, which is exactly what I wanted in set B. So I think this ends up being an optimal solution. So I get the number of elements in the union of A, B, and C is equal to, and let's go counting, 7 and 12 is 19. Plus 21 more is 40, plus 30 out on the outside gives me 70. And so I think those end up being my solutions, the optimal solutions. So I'll stop this here.